Hello and welcome to the Evergreen Building at the College of Southern Idaho in Twin Falls. My name is Sean Wilsey. I'm the geology professor here, and thanks for joining me today. We're going to do another video here on our Rock Identification with Wilsey series. We're winding down this video series, strange as that sounds. In another series, we've covered minerals. In this series, we've covered igneous rocks, sedimentary rocks. What we're going to do today is our first video exploring metamorphic rocks, and then in subsequent videos we'll look at some specific metamorphic rocks that will hopefully help you in your own identification of rock types. As always, the goal of our series and our knowledge here today is to help you be able to observe, characterize, and identify the rocks that you might be seeing on your own travels or exploits. But more importantly than just coming up with a name for the rock, we also, of course, want to be looking at the story. What is the process that formed these rocks? What exactly took place that created these metamorphic rocks? Because I think that's of much more value than just slapping a name on a given rock. I'll readily admit that this rock group, the metamorphic rocks, is probably my weakest set of rocks. I don't have as much knowledge and insight in metamorphic rocks as I do some of the other rock types. But nonetheless, I think I've got some fun things to share and some information that you might find helpful. So let's go ahead and get started. We're going to mainly be kind of covering some notes and some information here, but we will also look at some specific rocks as well. And of course, with our subsequent videos, we'll be looking at more rock types in person, which will undoubtedly be helpful to you. So if we come to the rock cycle, which is kind of where we started our whole exploration of rock types with the beginning of this series, we've covered igneous rocks, both intrusive, magmas that cool deep within the earth, and extrusive, magmas that rise to the surface, erupt as lava or ash or other materials to form extrusive igneous rocks, volcanic rocks. Rocks get exposed and broken down into particles we call sediments. They can eventually be deposited and buried and brought together to form sedimentary rocks. And we're looking here today and in this video at metamorphism and metamorphic rocks. This is kind of a hard concept and area of the rock cycle to wrap your head around because it doesn't take place at the surface. It's not erupting from a volcano. Much like our intrusive igneous rocks, these processes we're going to be exploring are taking place miles below the Earth's surface where pressures and temperatures are elevated. And so this is a little bit trickier concept to explore. Notice that the igneous rocks, both intrusive and extrusive, and the sedimentary rocks, all the little arrows in the rock cycle here, bring you to metamorphism. So that tells us that any of these given rock types, given the right sort of conditions, can be buried deep enough where they are subjected to the high temperatures and pressures that produce metamorphism. So let's move on and a couple other important points that we'll make here as we go along. So metamorphic rocks tend to form what we call the basement rocks, the very deep roots of our Earth's crust, deep below the mountains. Even wherever you're standing, miles below your feet, there are metamorphic rocks. So these rocks tend to form a lot of times the oldest rocks in the crust and also the deepest rocks. As we talked about, heat and pressure are the big driving processes here. So we're going to take existing rocks, any type of existing rock, and we call that rock that existed before it became a metamorphic rock, we call that either the parent rock, or another term you sometimes hear is protolith, so before. So the parent rocks can be any existing rock, and again, subjected to high enough temperatures and pressures, those will change into metamorphic rocks. This is an important point here. Metamorphism is a solid state change. It does not involve melting. Remember here, if we look at the rock cycle, if you completely melt a rock, you are back to magma, and then you're back to the igneous part of the rock cycle. So metamorphism is a solid state change. We are not melting the rock. There may be some tiny bit of melting that's possible with some of our higher grade metamorphic rocks, but basically we're changing the rock's texture or the minerals that make up the rock by the presence of heat and pressure. It could be that the rock's being squeezed in a certain way. It could be that the minerals that the rock was originally made of are no longer stable at the higher temperatures and pressures. So they break down and the elements recombine to form new minerals that are stable at those higher temperatures and pressures. And then this is sort of the temperature range we're looking at here. So what does it take to metamorphose a rock in terms of actual temperature measurements? You know, we're looking at 200 to 800 degrees Celsius, 400 to 1500 or so degrees Fahrenheit. You exceed these numbers here, and again, you're back to melting. Why is there such a big range here? Well, it depends on the original material, depends on what the original rock type was, what its mineral composition was, and some other factors that sort of dictates this. But this is the sweet spot. This is the temperature range at which most rocks will undergo a change that we call metamorphism. So let's go to where we actually see this type of thing taking place. What are some of the environments? So we're going to go over a couple different situations where rocks can become metamorphic rocks. The first one we'll look at here is what we call regional metamorphism. So this usually takes place over a big area. Like a lot of times it's related to a convergent plate boundary where the two plates are colliding and slamming into each other. As those two plates are brought together, the rocks in between are being squeezed. And so we would tend to get fairly high pressures, but maybe not as high temperatures in terms of how elevated those temperatures are, maybe more like moderate temperatures. So regional metamorphism will change rocks into metamorphic rocks over a considerably large area. Where might we see this today? Well, if you think about India and its continuing collision with Asia, which is forming the Himalayas, the big mountain chain at the surface, deep under the roots of those mountains, we could surmise that the temperatures are high enough and the pressures are intense enough that those rocks are being changed, even as we speak, into metamorphic rocks. And we'll look at the effects of that squeezing here in a minute. Another type of metamorphism that's possible is if you have some subterranean magma body, so a magma chamber or magma that's in the subsurface, the rocks that are touching that will tend to form metamorphic rocks, and that's what we call contact metamorphism. And so this tends to form very high temperatures because you have magma, which is upwards of 15, 16, 1700 degrees Fahrenheit, maybe something like 1000 degrees centigrade, but relatively low pressures because a lot of time contact metamorphism takes place at fairly shallow levels of the Earth's crust. This diagram here shows what you might see, and there's a lot going on here. So this down here in the bottom right corner, this is the magma body. So this is where the magma was in contact with the surrounding rocks. And so what we might see is this magma cools into granite. While this magma was still molten, it's changed the existing rocks. The limestone over here in proximity to the magma has been changed into marble. The sandstone over here, as you get closer to the magma body and the heat source, has been changed into a metamorphic rock called quartzite. And you can see that with some of these other rock names as well, which we'll get to. So there's a whole host of rock names in this sort of metamorphic zone adjacent to this magma body. But this would be a good example of contact metamorphism, where the magma body is in contact with the pre-existing rocks, and the heat from that magma body, along with circulating fluids and maybe some other processes, will change the rocks over time into metamorphic rocks. What are some other environments where we might get metamorphism? Well, you can just bury rocks, right? So if you just bury sediments or deposits deeper and deeper and deeper, eventually you can bury those materials deep enough that the temperatures and pressures are high enough that you're starting to enter that metamorphic realm. And so burial metamorphism, we might not expect super high temperatures or pressures, but they're enough many times to cause changes in the rock and become metamorphic rocks. And then this last one here, it doesn't happen very often, but it's fun to think about in kind of a exciting and sexy situation, and that's impact metamorphism. So if we have meteorites smashing into the planet, the speed of those meteorites combined with their density and their mass produces extremely high temperatures and pressures on the rocks that they run into, and you can get some interesting minerals and textures and features in these rocks. So this is what we call impact metamorphism. Definitely not as prevalent as the three we just covered, but it's fun. It's a fun one to talk about and think about a little bit. Okay, so Metamorphic rocks are going to be of mainly two types. They'll either be foliated or non-foliated. And what does that mean? Well, foliated means that the minerals are aligned, that the rocks have been squeezed, probably due to regional metamorphism or uneven pressure, and the minerals are aligned. And so here's an example of how that might look in an actual metamorphic rock. This is a metamorphic rock called gneiss, Gneiss. And we can see the obvious banding or layering in these crystals in this metamorphic rock. What these minerals define is a textural feature called foliation. So this is definitely a foliated metamorphic rock because the minerals are aligned in a planar or semi-planar fashion, defining this foliation texture. What we could then surmise then is that this rock has been squeezed on either side in this direction in order for the minerals to line up perpendicular to that. So we can look at the orientation of the foliation and then estimate that the pressure, the uneven pressure, came from a direction perpendicular to the foliation direction there. What we also sometimes see, though, if we don't see a preferred arrangement of minerals, that's just called non-foliated rock. So the rock may be squeezed and the crystals are kind of dense, but we don't see a preferred orientation of the minerals. So this is a nice piece of marble, and you can see that it's crystalline. If we rotate it in the light, you'll see some sparkles in there. This is totally made out of calcite, but you can see with the mineral crystals in this metamorphic rock that they're kind of randomly oriented. There's no preferred orientation. Therefore, this would be a non-foliated rock with no visible pattern or fabric running through the rock itself. So, metamorphic changes can be kind of slight. And let me just kind of illustrate a couple things here. So here what we have, this rock here is a limestone. You probably can pick out some of the shells. There's some fossils in here. These kind of web-looking things are called bryozoans. This is just a really kind of classic limestone with some fossil material in it. Of course, limestones, as we've learned in our series, are totally made out of calcite. So the main mineral that makes up a limestone is a mineral called calcite. But the calcite here is in the form of organisms, shells and hard parts from organisms that have accumulated on the ocean floor and then been compressed and compacted into rock. When this limestone gets metamorphosed, it gets heated, and now it's at temperatures and pressures where these organisms, these shells, maybe aren't as stable. And that causes the calcite in that to completely recrystallize and form a new rock called marble. But the limestone and the marble have the same composition and ingredients. This is totally made out of calcite. This is totally made out of calcite. The only difference here is the calcite has completely recrystallized to form this new rock marble. But if I hit it with the acid, it should bubble and fizz just like the limestone does, kind of confirming there that we have the calcite making up the rock itself. Another example, because these metamorphic changes can be kind of slight or they can be a little more prevalent. We've got this very thin, planar rock here. As I rub this with my thumb, it's very smooth to the touch. This is a sedimentary rock we've learned. This is called shale. It's kind of dull colored, it's fine grained, splits into layers. When this gets heated up just a little bit to fairly low metamorphic temperatures and pressures, it can turn into a rock that is also kind of dull colored. This one just happens to be a little bit darker, but it could be basically the same color. But it still has a lot of the same properties. It's fine grained. If you look at the crystal size, it's pretty small. It tends to break into sheets. Looks like it actually wants to break right now along that crack there. And this is a metamorphic rock called slate. So in this case, the shale to the slate change as we increase the temperatures and pressures a little bit doesn't seem to be that drastic. But if I take this same shale and exert even higher temperatures and pressures on it, I could get something like this gneiss. So this gneiss and this slate here has the same parent rock, shale. So those two rocks share possibly the same parent rock. The only difference here is the amount of temperatures, or the elevation of temperatures and pressures. This is a high-grade metamorphic rock. This rock forms when shale or other rock types are subjected to very high temperatures and pressures. So notice that metamorphic changes can be pretty dramatic, or they can be a little more subtle and a little bit more slight. Okay, so our last little bit of info here, if you're hanging in here with me, and I hope you are, is a broad classification of just metamorphic grade. We sometimes, out of convenience, refer to the temperatures that the rock was subjected to by using either low, intermediate, or high grade metamorphism. And these numbers here are just a pretty good approximation of the temperatures involved. Now, a good question to ask would be like, well, how do I know, let's say I found a metamorphic rock. I feel good that it's a metamorphic rock, but I have no idea if this rock is a low, intermediate, or high grade. In other words, I have no idea what kind of temperatures or pressures the rock was subjected to when it became a metamorphic rock. And to answer that, what we tend to use is this idea of index minerals. So what we have here, and I apologize, our color copier cut out this afternoon, so this is in black and white. I apologize, this is supposed to be in color. But what we have here is increasing temperature from left to right. So we can see low grade, more or less intermediate grade to high grade. And then we have a bunch of minerals, and we've covered some of these minerals in our mineral series. So some of these you might be familiar with, like the quartz, the feldspars, biotite, muscovite. Those are all minerals you may be familiar with, along with a few others. What this is showing us is that certain minerals, not every mineral, but many minerals, have a zone of temperatures in which they're stable. And so muscovite, for example, is going to be stable at low grade to intermediate grade metamorphic conditions. But as you increase the temperatures, muscovite will break down and start to form other minerals using those elements that it's made out of. Notice that garnet or sillimanite are associated with dominantly high-grade metamorphism. These minerals are not going to show up or even form until the temperatures are quite a bit higher. Some minerals like quartz don't help us at all because they're fairly stable at a range of temperatures and pressures. The feldspars, that's true of them to some degree. So what we use is we hope to see in the rocks, either in hand sample or maybe under the microscope, the presence of some of these minerals, which gives us some information about the temperatures in which they formed. So hopefully that's helpful. Appreciate you if you hung through this whole thing and learning a little bit about metamorphic rocks. Hopefully that's helpful. What we'll do moving forward is I'll get some of the rocks I have in my collection out, and we'll go through probably at least a couple videos, maybe 3 or so, maybe more videos on specific types of metamorphic rocks, their characteristics, how to identify them, what some of the variables are. So hopefully that's helpful. As always, you can support the videos by clicking on the little thanks button near the bottom right of the screen. There's a donate button at the top right of the banner of my YouTube page. Or if you go to the video description, there's links under there where you can keep these videos going. I appreciate everyone's encouragement and help and support in doing these. It's just fun to do. So with that, I'll sign off for now and appreciate your time, and we'll see you next time on another video of rock identification with Wilsey. That's me.